If you're a gearhead like me, you probably heard a lot about wind tunnels. It comes up in conversation all the time, whether it's race teams or OEM manufacturers doing fuel mileage testing. Well, have you ever wondered how they actually work? How do you build one? What's inside them? How do they measure these things that are so important? I realized the other day that I had all these questions and no answers to them, so we found a wind tunnel and we're gonna go check it out.
My name is Gary Eaker, and I am the designer and owner of the Aerodyn Wind Tunnel here in Mooresville, North Carolina, where we do almost exclusively NASCAR testing, both NASCAR the organization and also the individual teams that race for NASCAR. Behind me is the machine itself, which is an open return, as in an Eiffel style wind tunnel, which means that the important part is the red, the blue and the red, and then the huge warehouse simply allows the air to recirculate back into the front. When you say, what is a wind tunnel? It is essentially just a machine that blows air on an object and very, very accurately measures the effect of that air. So you say, okay, how do I design a wind tunnel? Well, first you tell me what it is you want to test. If it's an airplane, it's going to be a very, very large wind tunnel and it's going to have very high speeds. If it's a golf ball, it can be a very small wind tunnel and perhaps the speeds can be a little lower. In this case, since we're designing for a NASCAR car, the center section, which is the test section, is the most critical part. So you design the test section to be the right size. It's got to be small enough to allow a lot of speed as the air accelerates in, but it's got to be large enough that these walls don't restrict the airflow as it's flowing around the car. So it's a balancing act. So once you've done that, once you've got the right shape of the test section and you've got a car parked in there, you have to have that air entering smoothly. That's the function of the contraction, which is the blue portion. It starts off with a 4-to-1 contraction and smoothly accelerates the airflow to get it up to about, in our case, 130 miles per hour. And then as it goes through the test section and it empties out in the diffuser, that diffuser is slowing down the air in a very uniform manner. So it's not about quality of the airflow, but it's about recovering all that energy that you put into the air, because we've got 2,400 horsepower that we're putting into that air, and we would like to recover as much of that as possible. If we don't, we would have to have 5,000 or 6,000 horsepower to do the same job. The other thing is you don't see any fans in the front. The fans are all at the rear for a very simple reason. Air coming off the fans is really a turbulent mess. You don't want a turbulent mess coming into the test section for this car. You want the air to be very smooth and very uniform. So if you put the fans in the back, you're sucking the air through the honeycomb, and then it is very smooth and very well defined when it hits the car, and that's how you can measure it with that precision. The turbulence doesn't really do you a lot of good when you're in the testing phase. Yes, there is turbulence out on the racetrack, and that's unavoidable, but the turbulence is a big variable. We don't want large-scale turbulence because you never get the same answer twice.
This kind of works like a carburetor. Was that the Venturi effect, how it runs?
In a sense, although it's interesting you say that. Yes, you could kind of describe it as a Venturi, but it's exactly the opposite reason that we have a Venturi. In a carburetor, a Venturi is designed to generate a low pressure to suck the fuel up into the carburetor. We're not about generating low pressures, but we are about generating high velocities. Now, the two are related. As the velocity goes up, the pressure goes down. But we really aren't designing it to get a low pressure. We're designing it to get a very high speed. So it's kind of opposite ends of getting the same effect. But yes, it is a contraction, a small section, and then an expansion. So in that regard, it is similar to a Venturi, just not the same function.
So that stuff is interesting to me, like we're gonna get in all that like boundary layers and those kinds of things. That's the kind of stuff that I want to learn about and how you measure it, I guess.
Sure. Well, we could start off, we could just walk around here and talk about the contraction. It looks very solid until you're actually looking into it. It's really just very thick metal honeycomb. And of course the honeycomb is here to straighten up the air. As it's turning this corner and making a 180-degree turn, it's coming into here, and we want all the air to be very uniform. If you look at the shape, it's got kind of a hemispherical design to it, and that is because each one of these planes of honeycomb are pointed at where the front of the car would be. Think of it like a lens that is focusing the light. In this case, you can think of this as kind of a aerodynamic lens. It's focusing the air to get it all to come in at the right angles.
This is kind of like the stuff that you find in intake tubes of cars in front of the mass airflow sensor.
Yes, yes, for the same reason. Yes, you want to straighten out the air and make it as uniform as you can. In our case, you know, a vector has length and direction. So every particle of air is a vector. So if you looked at this thing as a field, you'd want every molecule of air to be coming in at the right angle and at the right speed. And this honeycomb controls the angle. The fact that we've got the 4-to-1 contraction ratio, that helps unify the speed as it's accelerating, coming downstream from the face of this to the test area. Now, since it's a 4-to-1 contraction, the airflow here is running at around 35 miles an hour. So you could stand in front of it and you'd feel a pretty good suction, but it's not uncontrolled. And then as soon as you get into there, obviously it speeds up. The last thing I want to mention is, you've heard several times now about 130 miles an hour. You say, well, gee, these cars are capable of running over 200. But you have to be very careful. Sure, we can build a wind tunnel, and other people have built wind tunnels that run 180 to 200 miles an hour, and that's great. The issue is that it takes a tremendous amount more power and more capital to build a big wind tunnel that does that. The question is, do you really need that? Well, that depends. In most cases, when you're trying to measure the aerodynamics of a certain object, as the speeds are too low, it's not really a legitimate, it's not qualitatively the same airflow. But once you get up to a certain number, a certain percentage of the full speed, all of the qualities of the air tend to straighten out. It's called the Reynolds number. And so essentially we've determined experimentally that the shape of the car, a full-sized car, probably has all these qualifying or quality airflow issues pretty well sorted out once you get on the north side of 100 miles an hour. And so from there, it's simply scaling the numbers up and down. So we take the 130 mile per hour air and scale it up in force to what it would be at 200 miles an hour, like you were running at Talladega, and it usually works pretty well. Horsepower required goes up with the cube of velocity. So if you're running twice as fast, it requires 8 times as much horsepower to generate that speed. So again, that's a big emphasis of why you really don't want to run any faster than you need to for testing purposes, to try to save energy, save money, and even the forces and everything. You're going to have a wind tunnel that is got more reinforcements in it and everything to generate that 200 miles per hour.
When you built this, did you have to calculate the size of the building that it was being put in as a part of the airflow measure inside?
Let me tell you, when you have an engineering staff of one, that's me, it's amazing the number of things you have to go through. I have always used Excel, the spreadsheet program Excel, as a tool, as a screwdriver, a hammer, and a wrench on how to calculate things. It's very powerful. And so I went through and I had a spreadsheet that said, okay, here's the expansion or contraction ratio, here's the test section speed, here are how many fans, here's the fan performance map, here's the diffuser angle, and here's the efficiencies. And all this stuff went into a rather large spreadsheet so that every time you change one number, say, what if I use 12 fans instead of 24 fans? Blah, 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 everything changes. And when I got all done and I said, okay, this is a design that meets the requirements for airspeed and energy and so on and so forth, I wound up with the design. Now, it's not magic. I had to put all these parameters into the Excel spreadsheet. But when it was all done, the Excel spreadsheet had an entire map of the dimensions of this tunnel. I mean, as in dots.
Really?
3-dimensional dots. And so this, I do not have a single CAD drawing of this wind tunnel. I have an Excel spreadsheet that has an entire cloud of 3D dots that essentially shaped what this wind tunnel was going to be designed. Remember, the the computer did not design that or shape it. It simply was marching to my orders of the parameters and everything. But the bottom line was I have all these three-dimensional points in space. You connect the dots just like you did when you were a little kid with a coloring book, and that's the size and shape of the wind tunnel. And that included how big this outer building had to be, what the velocities were going to be, because the recirculation velocities are only 10 to 15 miles an hour. That's what allows the building to be, if you pardon the expression, kind of crude. You see exposed I-beams and everything. But when the air is only flowing 10 miles an hour, you don't have to be particularly careful about streamlining everything. When it's running 130 miles an hour, you better be very careful about how you streamline things.
What is it actually made out of? Because there's not like a, you can't just go on Google and like how to build a wind tunnel.
Okay.
What did you choose to?
Okay, well let me start, let's do this right here. When you're building a race car, an airplane, or a rocket, it better be very, very lightweight. It better be made out of whatever materials you have at your disposal, carbon fiber, titanium, etc., etc. Wind tunnels are great big machines bolted to the earth. And even though there have been examples of people using high-tech materials, and once in a while it may be necessary, but for the most part, this wind tunnel is just a very big channel that's controlling the airflow. So using a lot of very expensive materials is not only unnecessary, but you have to remember, we did not have a big budget. And it took us a while to get the financing, even with all the money we brought up front and all the people, the grassroots level people who were helpful in making this thing happen. It still came down to, we had to be absolutely as economical as possible. We didn't build this thing out of high-tech materials for a very specific reason. It's the reason your car is not built out of titanium. It would cost $200,000, $500,000, I don't know what. But you build it out of the materials you need to get the job done. So we actually had some of the race teams laugh and say, gee, it looks like you went to Lowe's Home Improvement to get your building materials. And the answer is, well, actually we did some of our materials. The floor is concrete, that probably doesn't surprise you. The I-beams are all steel, because whether they weigh 1 ton or 10 tons makes no difference whatsoever. So the bigger skeleton is all I-beams, and then the smaller skeleton within the I-beams is all wooden spars. You know, this construction is really no different than say the floor of your house, where you have all of the runners and you apply the floor. In this case, we had to cut all of the ply, or all of the 2x6s with a curve built into it, and then we laid the plywood onto the curved spars of wood, and that shaped not only the contraction but the diffuser as well. Now, inside the wind tunnel, we'll get into the test section, that is a little bit different material. I wouldn't say it's high tech, but it's a different design and a different material than what you might expect. It's not using a lot of wood or even metal in this case.
Where did you learn all this stuff?
Well, I went to General Motors Institute. I'm a gearhead. I actually got my degree in engine design and thermodynamics, so I thought I was going to spend my whole career building engines and understanding crankshafts and cams and heads and all that. 1 year out of school, I got the opportunity to get into aerodynamics. I said, well, gee, at General Motors, there probably have to be 1,000 engineers that are working on engines. There were only 7 that were working on aerodynamics. So I said, I think I like my odds there. So I joined the Aero Group in 1977. The GM wind tunnel at the Tech Center in Warren, Michigan was finished in 1980. Before that, I had traveled to the Lockheed Wind Tunnel, to the Caltech Wind Tunnel in Pasadena, to the NRC Wind Tunnel up in Ottawa, Canada. So here I am at GM, and in 1981, a funny looking production car, which was really just a stock car from NASCAR, came in. And so I got the opportunity to start testing that. That was 81. So I became the stock car specialist for General Motors for all of the brands. And so I did that through 1994. And in 94, Hendrick was looking for a full-time aero guy. Nobody in the NASCAR business had a full-time aero guy yet. So they came and asked me if I was interested in moving down from Metro Detroit to Charlotte to work in as an aerodynamicist for them. Now, he asked me where I got the information and all my education from. I had a good, strong, very excellent engineering background. I had one introductory course in fluid mechanics, which is not going to be enough to get you where you're going. But between what I was learning, just being self-taught, just reading books and learning things and being interested in airplanes, and then of course having a whole lot of experience in the wind tunnel and doing airplanes. And the GM wind tunnel is a fantastic machine, but it's so much bigger and so much different, and it's designed for production cars, not for race cars. So I just, being an engineering geek, I'd say, gee, if I ever built a wind tunnel, it would look like this, it would do like this, it doesn't need this, it needs extra that. And so I kind of had some theories of what would make for a good wind tunnel. Like I said, when I got to Hendrick and they were interested, and by the way, I think Rick would have loved to have a wind tunnel on site. They had so many projects coming down the pike that the wind tunnel was simply way down the timeline. And I could see that it was going to be years before this wind tunnel was built. And I was hearing rumblings from other race teams about if we didn't build a wind tunnel, maybe they should. So that was enough stimulus for me to say, okay, my contract's up in '01. I got to build this thing before somebody else does. So that's when I went off on my own. And I'd had several years of design of what would the Hendrick wind tunnel look like. And so this was just a tweak. I had to save a few more bucks because I didn't have Rick Hendrick's budget. So a lot of the things in here are different. And in fact, that could have been a problem because when you're not building things the way most people build things, you have to prove that that works. And that was the beautiful thing about having racers and technical people to come and to test in our tunnel, because they don't care about mirrored glass and marble floors. All they care about is the function. If the wind tunnel works, they will come back. If the wind tunnel doesn't work, they're not coming back. And I said, fair enough. So they came in, they tested, they liked the numbers compared to the non-race car wind tunnel at Lockheed. That was designed for aircraft. The GM wind tunnel in Warren, Michigan, that was designed for production cars. The NRC wind tunnel up in Ottawa was kind of an all-purpose tunnel. Those tunnels are a great design, exactly what they're designed for, but their one weakness was that a good race car wind tunnel has to have very good boundary layer simulation along the floor, because the race cars are very close to the ground and they depend upon this airflow under the car for a significant portion of their aerodynamics. And the other wind tunnels just really weren't designed for that. So I said, well, I've got an advantage right there, not because I'm smarter, but because I'm designing this for race cars. They didn't design theirs for race cars.
That is interesting. We're going to get in there and see that. But I got a question about this. You got air-to-air intercoolers for...
Absolutely.
What is this doing?
Okay, well, you know, along the way, we've had several different modifications. The main principle for the boundary layer control has always been the same, but the details, it's kind of like the next model car that has more features than the last. So we're on our third generation of floor, the principle always being the same. You'll see it when we get in there, but basically we have jets of air keeping the air moving, because the air wants to slow down and stall. That's what a boundary layer is. We don't want a boundary layer, so we keep energizing it and blowing the air along there. This is the latest, I guess you could say Gen 3, that we have a compressor in here that is blowing air into the floor in just a certain area, which we'll look at when we get into there. This compressor, as you probably know, anybody knows anything about turbochargers, they always add heat to the air, always. And we don't want hot air being injected into this. So this small compressor, and you can see these are silicone boots and everything, they're simply blowing the air into this. This is no different than an air-to-air intercooler in a turbo. The only difference is we have the luxury of making it big and not worrying about how big it is. So we have these 4 intercoolers. We have this fan, which looks like a unit that would come off the top of an AC unit outside your home. And so by having this air-to-air intercooler, we're able to inject the air within 2 degrees of ambient temperature, which means now we don't have to worry about temperature differences spoiling the effect of our jets.
Is that your main air conditioning unit right there?
That is one half. The other half is on the other side.
That's half?
Yes.
How many tons is that?
Are you talking about cooling capacity?
Yes.
Yes, your typical home has a 4 or 5 ton air conditioner. Our wind tunnel, remember this is cooling capacity, not the weight of the machine. Our air conditioner is 250 tons of capacity. And in case you didn't know, a ton of refrigeration capacity is exactly, the reason they named it that is, you take 1 ton of ice and melt it over a 24-hour period of time. The amount of heat that it absorbs is 1 ton of refrigeration, 12,000 BTUs per hour.
I did not know that it came from a measurement of ice melting. That is interesting. Yes. That is some serious, man.
Well, let me tell you, when you got 2,400 horsepower, plus we've got more, this stuff that's all going into the floor. So altogether we have probably almost 3,000 horsepower worth of air being moved. And it's not free. I mean, you know, of course, it takes electricity. Well, thermodynamics says all that volts times amps turns into heat. I mean, I don't care if your fans are 100% efficient, it still turns into heat. So the way I describe it to people is, why do we need an air conditioner in here? Because the amount of energy we're putting into the heat is about equivalent to, you know, the small radiant heaters that you might see around the house, just the little local heaters that keep your feet warm or whatever.
Yeah.
Plug in 1,000 of those and tell me if it's going to generate any heat. That's what we've got going on in here. So we've got to pull all that heat out of this building or it gets really, really hot. Originally, because of our very austere budget, we didn't have air conditioning. We had just air exchange. If you look down at that end and you see that hole, that big black hole right there,
yeah,
that is air that's coming in and getting blown in here. The air's coming from the outside. In the spring and the fall and certainly in the winter, that's fine. In the heat of the summer, we're pulling in 95-degree air. That's the cooling air.
Yeah.
So you can imagine the heat in the wind tunnel, it might be 110 degrees in here. The car's fine with that. It doesn't hurt it technically, okay? We can blow 110 degrees and get accurate information. But the human beings who have to work in here aren't terribly delighted to be working at 110 degrees. And once you get into there, in fact, even if you add some of the other heat issues and all that, we might have the floor, the aluminum on the floor might be 120 degrees. It's actually, you put your hand on 120 degree aluminum, it's not going to burn it, but it's not very comfortable.
Yeah.
So yeah, there's a lot of factors beyond just the technical to try to make all these things work.
Yeah, this is stuff I never knew about, never would have thought about.
Yeah.
Everything out here is things that you never see, because you see pictures of cars inside these things all the time.
Sure. Now before we go in there, there's the pedestrian door. You're not going to get a car or anything of any size through there.
This is one of the questions I had too.
What do? You build a door into the side of the diffuser. It's kind of a big door. But you can see it's on hinges. It moves easily. The car rolls in through the big door, and then we lock it up and away we go. Now as we're walking in, stop and look at the wall on edge. You'll see that it's not straight. Most wind tunnels do have straight walls, and that's fine. We have curved walls for a reason. You know, one of the biggest technical challenges of wind tunnels is that a wind tunnel that has parallel walls has perfect airflow. As soon as a car or anything else gets plugged into it, it's not perfect airflow anymore because it's kind of plugging up that section. Now, in our case, we had the great luxury of having a well-defined test object, that is a full-size race car. We knew what was going to be in here day in and day out, so we had the luxury of saying, we should not design these walls to be parallel. We should design these walls to have curvature. The next question is, how much curvature? It's not as simple as this, but in principle, it's simple. What you do is you say, okay, the air entering the wind tunnel, the walls are about 18 feet apart. If you were out on a racetrack all by yourself and flowing through the air, what would the air do plus and minus 9 feet from the center line of the car? As the air is going through, or the car is going through the air is expanding gently, moving around the car. So if you could see this car as it's driving down the track and say somebody ahead of it had some smoke, you'd see the smoke is not running straight down along the center line of the car. It's moving away from the car, and then after it gets past the car, it starts to collapse around it. So it's a very, very subtle teardrop kind of a shape. And so we could use some calculations and say, what would the airflow look like this far away from the car? If we can duplicate that on our ceiling and on our walls, we have no blockage effect. And blockage effect, as I said, is a huge issue theoretically and practically. So you could say it this way. In a lot of other wind tunnels, they have to correct the airflow mathematically because they have parallel walls. We are correcting the airflow mechanically and physically, so we don't have to use any mathematics to correct the airflow numbers once the air is coming in the wind tunnel. And if you've done it right, it's going to give you the correct pressure profile. So we've proven that. We've gone out on the racetrack and on the test tracks, and we've put pressure taps all over the car. If the pressure's, force is pressure times area. And if the pressure profile around the car is the same as the pressure profile in the wind tunnel, that's very strong evidence that you've done it right. And we have done that, and we've gotten very good results. Now, one other thing is you'll see all these stripes. That is not, that's not for aesthetics. In wind tunnel design, there's also something called a slotted wall tunnel. What it is it's a tunnel that's mostly solid, but it has vents in the walls. We started off with slots in the walls that allowed the air to breathe, so that if we didn't get the shape right, it would give the air somewhere to go. It wouldn't be forced to stay constrained by these walls, so it would allow it to breathe. Now, that was just an insurance policy. The plan was to not have a slotted wall tunnel, but in case somehow we got the shape wrong, there are slotted wall tunnels out there which do a fine job. The other thing is that we knew that if we did it right and there's no air breathing across the boundaries, we could block this off, and guess what? We'd get the same results. And we did. That was another way of proving that we had the shape right, is we put these aluminum covers over the slots. The only variable was not the quality of the numbers, is we saved ourselves a few horsepower because of the extra parasitic drag of these slots. So that proved to us empirically that we had the right shape in the tunnel.
Is it just me, or did you always think that the fans were at the front of the car? I didn't know they were in the back. So what is going on back here?
Well, behind me you see the 22 fans. Now again, these are at the rear, so they're pulling the air through so it's nice and smooth. It's interesting because before people see the geometry, they know the math. You say 22 and they're kind of like, 22? Where do you come up with that? Well, it's easy here. You see 1, 2, 3, 4, 5, 6, so there's 18 fans in a rectangle and 4 more fans in the top. That makes 22. Each one of these fans is about 100 horsepower. Interesting fact, these are not the most efficient fans you can buy for this size. You say, well, why not? Because we wanted the quietest fans, because we're not sure how close our neighbors are at 2 o'clock in the morning, what they might hear. We don't want the police to knock on our door and tell us we have to shut down because of noise ordinances. So we got fans that were almost as efficient, but they were quieter. So as far as the wind tunnel goes, this certainly is not whisper quiet, but there are louder wind tunnels around, and certainly once it's encapsulated by the outer building, you hardly hear anything from the outside. Each one of these, if you're a gearhead, I'll just give you a reference, a small block Chevy. If you turn on that motor, it's generating as much torque as a good size small block Chevy. Not as much horsepower because it's only running at 1800 RPM, but it's generating well over 400 foot-pounds of torque to get that thing spinning. On one end of the spectrum, you have a Walmart box fan. Moves a lot of air, can't take any pressure at all, just stall it right out. At the other end, you have a compressor for putting air in your tires. You can't stall it out. I mean, it'll make 100 PSI, but it doesn't move any volume. So the real trick, the real power requirement is when you have a lot of volume and you need to generate a lot of pressure. And that's what these guys do in order to give us the capacity to run. I mean, we can run over 130. If we had the thing all the way pedal to metal, we could probably run almost 150 miles an hour. But again, 130 is a sweet spot. It gets us all that we need.
You ever had any since it's doing sucking, you ever had anything fly off a car and go?
Fortunately, nothing big. The worst case scenario, it sounded worse than it was, but somebody had a metal, like a yardstick, but it was long. It was sitting on top of the car. So on edge, you could hardly see it. So the wind came up, it blew down here, it slid underneath this screen and wedged between the annulus and the fan blades, and it made a terrible racket. So everybody immediately hit the stop and went out there. I said, don't touch it yet, it's probably really hot. So it did some very, very minor damage, but that's why you can see now we have a metal catch fence at the bottom, so nothing sliding along the floor can get underneath it.
Huh.
In this tunnel, you never have to worry about a car escaping, because the car is literally bolted to the balance that goes down to the floor. It's not supported by the tires.
I've always wondered how you anchor the car in here.
Yes, okay. Well, let's get into the balance. First of all, the balance is in the basement. And that's pretty typical for most tunnels. Remember, the primary feedback, the thing that tells you that you're doing the right work in the wind tunnel, is pressures are something that's used, and flow visualization, which can be done in the form of yarn tufts, it can be done in the form of smoke and all that, is another form of feedback, but by far the most useful and the most precise feedback is force measurement. Now, in a wind tunnel, or excuse me, not just in a wind tunnel, but in a car or in any object, in an airplane, in anything that moves, you have three axes. You have height, width, and length. So of course you have drag going this way, you have side force going this way, and you have lift going this way. That's not all the equation. You also have three moments. That means a torque that's trying to rotate the body. So about the drag axis, you have a roll moment. About the lift axis, you have a yaw moment. And about the side force axis, you have a pitch moment. So we have what's called a 6-axis wind tunnel balance. So that means that at the same time, we're measuring drag, side force, lift, yaw moment, roll moment, and pitch moment. So this balance is delivering 6 different numbers that are telling you about how the air is trying to move or put forces on your car. So in our case, well, first of all, you may know, if anybody who's a wind tunnel or race car fan has heard of a rolling road. A rolling road, just imagine a belt sander turned upside down with an HO car on it. That's a scale model of a rolling road. So you have a very large sheet of, typically, if it's full scale, it may be stainless. If it's a reduced scale, it may be a fabric or something like that. But you have this floor, and of course the idea is that when you're going down the racetrack, the air is stationary, the racetrack is stationary, and the car is moving. Here, of course, it's the opposite. The car is stationary, the air is moving, and remember, since the air is going at the same speed as the track, which is 0, in this case, we need to have the track or the floor going at the same speed as the air. That's a rolling road tunnel. And most, in fact, virtually all race car wind tunnels have rolling road tunnels, rolling road floors. And I said, well, that's fine, but again, not only am I on a fixed budget, but we use fans everywhere else to manipulate and move air. Why do we have to have a great big plate moving at very high speeds to move the air? Why can't we do it with fans? So that was the concept. And by the way, this isn't totally original. There's an old patent from 19-something where they were talking about moving air. You also see on airplane wings, and NASA has worked a lot on jets and things blowing air over wing sections to try to manipulate the boundary layer. Remember, a boundary layer is just dead air along the surface. When you have air above the surface that's moving, along the surface, air has viscosity. That sounds hard to believe, but just like maple syrup, air has viscosity. It's just not nearly as obvious. But this air along the stationary surface is dragging down and slowing down and stalls. And as it stalls, then essentially it builds up. So what you wind up with is at the front of the test section, if you have no boundary layer control, you have a super thin boundary layer, and it doesn't really make a lot of difference. But as it continues, it's growing. It's like a little ramp of dead air that's getting thicker and thicker and thicker. That's not what you want. So in some wind tunnels that don't have this sophisticated boundary layer control system, in the very front, some wind tunnels suck away the dead layer of air, like a cheese slicer, and that works. Some tunnels have jets that blow air and energize the boundary layer. So it's crazy, but suction and blowing are actually both providing some source of
it's like any kind of external stimulation,
yeah,
besides doing what it naturally does.
Right. So either one of them is either energizing the air or getting rid of the bad air, and either one works. The problem is this: blowing air is adding extra mass flow that's really not natural. Suction is actually taking away mass flow, and that's not really natural either. What if you combine the two? Then you wind up, if you can blow and suck the same amounts of air, you're not adding or taking away any mass flow. All you're doing is adding energy. And after all, since a boundary layer is an energy deficit, if you can add energy without having to have a huge machine that moves the floor, then all the better. So this entire floor is just a mechanical answer to trying to give us the right boundary layer, which is 0 thickness. So no matter how low you get to the ground, you should have the same velocity as you have 3 feet off the ground. Now, if we come up to the front, and we have, you can see from this, we have many different portions. It's just like an engine. You can talk about an engine being a piston, a connecting rod, and a crankshaft. Well, that's fine. But until you understand heads and cams and valves and lifters, I mean, it's a whole lot more complicated than just a piston running up and down. So by the same token, this floor is a whole lot more complicated than just slicing away the air and replacing it with fresh air that's moving at speed. So in this case, the very front layer is just a massive vacuum cleaner. It's sucking away the dead air that's already built up just at the even before you got to the test section. However, guess what? It's relentless. As soon as you suck it away, it's starting to build up again. So, but you can treat the air differently far away from the car than you can close to the car. Far away from the car, you can be a little bit more crude. Once you get up close to the car, you have to be very precise about how you do this. So we suck away a big chunk of the air, and then you can see all these slots, 1, 2, 3, 4, 5 slots that are each sucking away a little bit more air incrementally to keep it thin. Now you have a forward-facing suction slot and a rearward-facing jet that is going to not only suck away the air, but now since you're getting kind of close to the car, you have to replace that air. So we have the jet moving to do that. We have another one here. Then you can see when we get down here, all the holes that you see are suction holes. What's not quite as obvious is on the rear here, there's a very thin opening, and we have air blowing out of that tangentially, which is speeding up that air. So I say that aerodynamically, if you ever into a big box store and you see like a conveyor belt kind of thing, but it's passive. It's got like a bunch of rolling pins, right? Mm-hmm. And you roll the box and it kind of frictionlessly rolls down the ramp, right? Mm-hmm. No friction. Well, think of this as an aerodynamic or pneumatic answer to that. It's kind of sucking away the air and blowing more air. So you have these couples of suction and blowing, boom, 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 virtually down the whole length of that. Now, in the early days, this place was designed in the late 90s, and we started building it in 02. The Cup cars had a sharp-edged valence, but they didn't have a whole lot of stuff going on underneath. And also, they weren't running a 1/4 of an inch to ground, so everything was fine. But once we got into the later generation cars, where they're getting closer to the ground and they're starting to shape the front underbody, well, this floor was good. It was good down to about a 1/2 inch. These guys are sometimes running a 1/4 of an inch or less to the ground when they're testing, because that's what they're running at the racetrack. And that's what this segment is for. This is the latest and the greatest. I'm not sure if we'd ever build the entire floor out of this. If we did, it'd be fine, but it would have been extremely complex. But this is essentially just the next generation. The compressor that you saw outside is feeding these.
Just this?
Yeah, so you can see the very tiny holes here. And then in the back side of that, there's something called a Coanda effect. Only aero geeks really understand that, but essentially it allows the air to turn a full 90 degrees. So we have the jets coming out here using the Coanda effect, but it doesn't require any of the surface to be raised above the flush floor. So this has worked out very well. We've gone out on the track and gotten very good confirmation that it's doing the right job. So here you can see we've got the car, we've got tires that can go on rollers. And so this is a a roller that's got electric motors on it, and it also it automatically adjusts for camber. It's on a pivot. So the tires are sitting on the rollers, the tires are spinning at the same speeds as the airflow, so it gives more accurate simulation. The other thing is, if you look at all these arcs, one of the things that all cars in wind tunnel, of course, they have the option of going vertical, but all wind tunnels have what's called a turntable, and that allows the entire object, whether it's an airplane or a car or whatever, to yaw, you know, to steer from side to side, because when you get out on the racetrack, when they're going around the corners, there is some yaw imposed in those. They're going around the corners at 2, 3, 4 degrees of yaw. The back end kicked out. It's controlled, but the back end's kicked out a little bit. So we simulate that. But if you look at these arcs, as far as I know, everybody else yaws the car about the center of the wheelbase and the track. We yaws ours about the front axle center line, because the front, believe it or not, actually controls the yaw performance of the car, not the back. It's not like a weather vane. It's not like the tail of an airplane. This doesn't have those. So it's really controlled by the front of the car. So that means that the nose of the car doesn't move very much side to side, which is where the most critical part is. Some people have expressed some concern that the back moves too far, but we've proven experimentally that's not an issue. So that's the funky shapes that you see. And again, we won't have a full yaw table because we need to have all this to be controlling all of the boundary layer flow control.
So if you didn't have the wheels spinning, how much does does the actual rotation of the tire do, like with its own boundary layer and creating turbulence in the wheel well?
Call that windage. When you have air that's entrained like a crankshaft, it would have windage, right? There's windage around the tire that's real. And so, yeah, if we didn't have that, that might change, you know, the numbers a few percent, but it would change the balance a few percent. So it would just be a one step away from the right simulation. We have several hundred pressure taps embedded in the floor. So every run, the race teams can look at the floor and look at the pressures and see, based on ride height and whatever modifications they've made, without even having to add pressures to their car. They can use our wind tunnel to look at the profile of the pressures under the car and say, aha, it's making more suction here, it's making less suction here, that's affecting the pitch moment, et cetera, et cetera. So that's another piece of information that they get on every run.
Are these fixture points, did you pick something that's pretty common on a cup chassis that everybody would be able to use?
Yeah, now of course that's changed now with the newest generation. But essentially what we had to do is we had to get something, you know, with the structure, you have to make it stiff, but you also have to make it aerodynamically transparent, all right? Well, in the front, you can see it's behind the front tire. So it's in the wake of the front tire. So the fact that we have a strut here has virtually no effect. I mean, we've actually measured it and they've simulated it. The effect is minute. It's a tiny, tiny fraction of a percent. So it's in the wake of the front tires. Now in the rear, you say, wow, it's ahead of the front tires. But you know what? You don't have a wake, but anytime you have an object and the air is approaching this object, the air is slowing down. You have what's essentially called a stagnation point, where the air actually deadheads against the surface and then it splits around it. So we put these as close as we could to the rear tires for the same purpose, so that the air moving along here is not moving nearly as fast as it is further forward. Plus it's still more or less in the wake of the front tires. So these struts have very little effect on the airflow.
So with this being placed here, is that kind of like whenever you're shoveling snow and the shovel fills up with snow and then the snow starts to go, you get a big pile in front of it and gets pushed around, it doesn't even touch the shovel?
Yeah, in a way, I guess I've never heard that snow analogy, but yeah, in a sense that works.
I did a lot of shoveling snow.
Yeah. Well, in the front of the car, or again, even if you look at a Boeing 747 or you look at a race car or whatever, they've always got a stagnation point. Theoretically, there's one point where the air just goes dead, but you can think of it as a separation, it's like, I know what it's like. It's like out west, you know, they have the Great Divide where everything, you know, the Continental Divide, where everything west of the Continental Divide flows into the Pacific, and everything east of the Continental Divide flows into the Atlantic. Well, it's the same kind of thing. Is everything north of the stagnation point flows over the car, everything south goes under, everything to the left goes this way, and everything to the right goes that way. So you have one tiny spot where you have the air that's actually deadheaded. And then everywhere else, in a small region, it's moving slowly, and then as you get closer and closer to the edges, it's moving faster. An airplane wing has the stagnation point in the center of it, but then very quickly it accelerates over the top, and that's what gives the airplane wing lift.
When you were doing aero development on cars, was there ever anything that you either ran through a simulation or just in your head that you're like, okay, this is going to do that, and then you test it in a tunnel and it did something completely different that just blew your mind? Didn't seem to make any sense.
That's not news. That's not news, okay? What you just said, okay, imagine this. Let me flip it on its head. A lot of people are parents. Well, did you ever have your children that they did something that wasn't totally textbook, that wasn't totally, did anybody ever do anything unpredictable? I mean, that's kind of an absurd question. It's like, are you kidding me? So in the case of aerodynamics, I tell people, here's what I say. I say, you know, okay, I've been around this business. I've been doing this for 45 years. Some people would call me an expert. You know how much I know about aerodynamics? I know about that much about aerodynamics. But you know what? Most of the people know that much about aerodynamics, so I still look pretty good by comparison, okay? So there's still a lot of stuff. And in fact, if anybody had all the answers, we could tear down all the wind tunnels, right? But the flow is very complex. And of course, it's built on years and years of experience, but okay, you come up with a new car, a new geometry, a new combination, you kind of pull the rug out from under you. Look at a team as impressive and with as many resources as Mercedes-Benz in Formula One. They were just killing it all these years. And then, you know, at the beginning of last year, they came out and the car was, I don't know all the details, I think some of it was what they call porpoising, which is the front and the rear, and the aerodynamics underneath, and the dynamics and all that. But the bottom line was, as smart as they are and as many resources they had, they didn't get it exactly right. I mean, nobody does get it exactly right, but the people who get the most right, I remember Harry Hyde saying, well, the person who wins a race is the person who makes the fewest mistakes. Well, that's kind of the case. So nobody gets it exactly right, but you get as much right as you can.
Where do you actually monitor this stuff from? If you got a car in here and you're running it, where's the control center at?
Okay, well, it's on the other side of the walls, and I can show you that. We're now in the control room. The operator, the person that works for Aerodyn, sits in this chair. There's all kinds of information that's telling the operator what is going on, and to make sure he's monitoring everything, to make sure temperatures and pressures and speeds and everything are exactly what they're supposed to be. The person in the race team who is controlling the data, at least measurements and so on, has those monitors over there. And then all the technicians and people who are working on the car, they don't need as much detail, but you know what? They're smart and they understand what these coefficients mean. So we've got a little theater for them. So we display all this data up on the big screen, and they can look at the progress of the test, and they can see even before they're given marching orders which way the test is going and what they're probably going to be doing for the next test. So everyone, not just the engineers, are involved in the process of reading the information, interpreting the information, and getting ready for the next test. Aerodyn is not in the business of developing anyone's car. In fact, we do not get involved at all because we have different teams coming in here every day. If we try to make any recommendations to them, the team that just left would say, hey, that was our idea and now you're passing along to somebody else. We don't do any of that. We provide the best facility we know how so that they can come in with their ideas and their manpower and woman power and all the things they've got to do to make their car the best we can. We just have a facility that's extremely repeatable and has a pretty good fidelity to the real world out there.
How efficient is the HVAC system in your house? Are you like tweaking little things on that too?
No, actually, okay, in this case, no. We have had houses, like for instance, we had a house that had a very tall ceiling and it had a loft, and the airflow was not the airflow, but the temperature control was terrible. And so I told my wife, I gotta do something about that. She says, no, don't do that. Call the professionals. I said, Deborah, the professionals designed this and it didn't work. So excuse me if I'm too presumptuous. I think I can handle this. So yeah.